Hello, everyone. This is Gurumurthy Ramachandran again. And in the past few lectures, we have been discussing various exposure models. And then we also discussed the idea of uncertainty analysis and how parameter uncertainty translates into the uncertainty in model outputs. And what we are going to do today is talk about applying both modeling and uncertainty analysis in two different examples. The first one is in an application in reconstructing historical exposures. This is frequently done in the context of occupational epidemiological studies, where we are trying to reconstruct the exposures of different groups of workers over a long period of time. And the exposures are, it is hypothesized, causing some health outcome that is apparent today. So in this example, what I'm showing on this slide is the exposures to one similar exposure group of workers over a period of time from 1956 all the way to 1979. So this is the period in which there was a lot of transition in the way exposure measurements were made, and for which we have fewer measurements than the later periods from 1980 onwards. So here you can see that measurements were made using three different instruments. In the earlier periods, an instrument called a conimeter was used that measured particles and particles per cubic centimeter, PPCC units. And you can see that, for example, from 1956 to 63, during that entire period, only 24 measurements were made. That's the highlighted number in parentheses. The mean is 959 and the range is 765 to 1,153. So the conimeter measurements are personal measurements made in the breathing zone of the worker, but they are instantaneous measurements. So they are made over a period of like a second or less. Then we move on to the high wall measurements. So these are instruments that are fairly large, driven by large pumps, and they are area monitors. And so they are actually measuring something different. They're not really measuring the personal exposure of workers. Again, these are, for example, from 1964 to 66, only one measurement was made, and 67 to 71, only two measurements were made. And then there were more measurements made in 1972 through 75. And then starting in 1976, we come to what is now the standard, which is the personal measurements measured with a personal sampling pump. And it is measuring exposures in units of mass per unit volume, or milligrams per cubic meter. You can see that there is a lot of variability in these data, and there are also, for many periods, just a very few measurements. And so if we look at the uncertainty in these measurements, they arise from several different sources. One is the analytical variability itself, which we have discussed in the course. So there's random measurements. And then if we want to convert all of these measurements made using different units and different types of instruments, we need to really obtain conversion factors between these different types of measurements. And so there is a lot of error in those conversion factors. There is also environmental variability, spatial and temporal variability, and between and within worker variability that we have discussed previously in the course. And finally, there are systematic biases. So if we account for all of these types of errors, and I'm not going to go into how we did that, we come up with an exposure history for this SEG as shown in this graph. And I would like to point out that the vertical axis here is a logarithmic axis going from 0.1 to 1 to 10 to 100. And we can see that the error bars are enormous, resulting from very few measurements over an extended period of time, and also the large analytical errors and the conversion factors between these different instruments. And what it boils down to is that these measurements by themselves are really not very useful in characterizing exposures. And the estimates of exposure with such large error bars are not very useful for developing quantitative dose-response relationships in epidemiology. And therefore, we need to supplement the data with historical information about workplace conditions, expert judgments, and exposure models. So in this case, what we did was we asked experts to give us inputs to exposure models. So this is called the direct elicitation of expert judgment. So we asked an expert to directly give us the subjective probability distribution of exposure. And this subjective assessment is a complex decision resting on a hierarchy of assumptions. And this direct elicitation hides the rationale behind the decision-making process. So this is one way of doing expert elicitation. And the result of such direct elicitation is that the experts themselves could be biased and could provide incorrect estimates. So we want to combine expert judgment along with modeling because it is better to disaggregate the judgment by modeling each individual aspect of the problem. And many people, including Morgan and Henry, have shown that when you use a model to elicit expert opinion, it produces judgments that are closer to the truth. So in this example, we're going to use this simple model that we are all very familiar with, the well-mixed room model, and also the steady state or equilibrium version of that model. So the equilibrium concentration is given very simply as the generation rate, or in this case, the aerosol mass generation rate, G, divided by the ventilation flow rate, Q. The generation rate itself can be estimated by the product of, in this case, an intermediate product that is called Bessemer matte production rate. So this is in tons per minute. And then the emission factor in terms of milligrams per ton. So Bessemer matte production is something that companies and nickel production facilities do keep track of because this is a measure of how much stuff they are producing. And the emission factor is how many milligrams per ton of Bessemer matte becomes airborne. So this is the generation rate or aerosol mass generation rate. This is a nickel production facility, so they are extracting nickel from nickel ore. And we use two experts in this example, and they are both relatively familiar with nickel extraction processes already. We also provided them a nickel smelting operation description, process flow sheets and layout maps, ventilation surveys, emission factor information, and production levels of Bessemer matte in terms of annual production level. Here are the probability distributions for these input parameters. So on the top left-hand side, you see the production rate in thousands of tons per year. And this is for 1 year. We know that the production was somewhere between 314 and 347,000 tons in that year. The top right-hand side graph is a uniform distribution of the emission factor. So how many kilograms of aerosol are produced per ton? So it's somewhere between 0.1 to 0.3 kilograms per ton. On the bottom left-hand side, we have the probability distribution for the ventilation flow rate. And again, it's between 100 and 200 cubic meters per minute. And these are all distributions that were provided by the expert. And using these uniform distributions for the three parameters in our model, we can run Monte Carlo simulations like we have discussed previously. And what we get as the output of the model is the probability distribution of the airborne concentration in this part of the nickel processing plant. And we can see that, as in previous examples, this follows a log normal distribution. And so this is the exposure estimate along with its uncertainty for 1 year during this period. And we can extract error bars from this log normal distribution. So what this graph shows is the expert opinion estimated exposures for each year in the time period from 1959 to 1979. And on the horizontal axis, you have the inhalable nickel concentration in units of milligrams per cubic meter. And on the horizontal axis, you have the years. And this graph shows the exposure history according to two different experts who were provided with the same information. And they provided slightly dissimilar input parameter distributions for each year, as we have discussed on the previous slides. So the main thing to note here is that the two experts are not that different from each other. Although one expert, expert two, seems consistently higher than expert one, although not in a statistically significant way, except for the earliest 3 years. So now we come to this graph, and what I'm showing here is again on the horizontal axis the years from 1959 to 79. On the vertical axis, we have the inhalable nickel concentration in units of milligrams per cubic meter. But what I'm showing here for each year are three different things. The triangles are showing the exposure estimate if we just use the limited data. And these are from the same graph I've shown you earlier, where we have these enormous error bars that make it virtually useless for the purpose of exposure reconstruction and epidemiological analysis. And then we have the solid and hollow diamonds. Those show the exposure estimates from the two experts, along with exposure models and Monte Carlo uncertainty analysis. And so we see that we have reduced the uncertainties tremendously so that we have now an exposure reconstruction that can be actually used for epidemiological analysis.